Okay, today we're going to start talking about vectors, and there's actually a couple of lessons here in Chapter 8 about vectors. The first lesson, 8.3, is looking at a vector through your geometry eyes. And then the next lesson is using vectors in an algebraic form. So as we start lesson 3 here, we're going to start with some basic terminology. Then we're going to talk about something called the equilibrium. You're also going to have another word. I don't see the word resultant in here. That's an important word, but the equilibrium, which has to do with a resultant vector. Then we're going to try to do a couple of applications that deal with vectors. And he points out to an incline, like if you're on a ramp, or navigation, a boat moving, or a plane moving. All right, let's see if we can fill in these blanks with as many of these vocabulary words that are up here. It's one thing to talk about the words, another thing to fill in a blank. Okay, quantities that involve magnitudes, such as 45 pounds or 60 miles per hour, can be represented by real numbers. We call those scalars. Scalar. Okay, they're like, it's just you say 40 pounds. You're not saying 40 pounds pulling down from gravity. You're not saying you're throwing a ball that's 5 pounds and you're throwing it to the west. You're not saying which way it goes. It just talks about the numerical value. Other quantities we'll call those vectors. That's what this section's about. Vectors, called vectors. I don't know why there's two blanks. I can't make up a word. Maybe called a vector, maybe, I don't know. Yeah, probably called, I'm just going to say vectors. They have magnitude and direction. Okay, we'll look at like an example in a little bit. Okay, a vector quantity can be represented with a directed line segments. That means this. I'm going that way and I'm starting here, or I'm going that way and I'm starting here. It gives you a direction. Uses an arrow to indicate direction called a, well, the arrow, it's a good one. What do you call the arrow? I don't see, let me see the words up there. Well, I know we're going to have initial point and a terminal point, but I don't know, those will go down here. Okay, arrow to indicate. Not sure what arrowhead is called. I know it indicates directions. I just drew one right here. A point and a point. And it isn't too uncommon to say, this is starting at A and up here is B, means it's starting at your initial point and your terminal point is where it's going. Okay. Vector, I still can't figure out what the direction is called. I mean, the arrowhead is called. The length of the vector represents this one I know, magnitude. How long is that vector? That magnitude is longer than that magnitude. So the magnitude is larger than this magnitude because it's longer. And so when two letters name a vector, the first letter indicates an initial point. That's one of the vocabulary words up there. And the second letter we use Oh, I should have, he wants it on two words, initial point. And the second letter represents the terminal point. Yes, the arrow usually in mathematics say it keeps on going, but a vector doesn't. When I stop that vector at AB, it's that's how long it is, and this could be OP. Well, we put P up here, OP, and that would be the magnitude of OP, and I'll do it with really dark letters, which is the same thing as saying OP with an arrow on top, like a ray. And you've done that before in geometry. Okay. Two vectors are equal if and only if they have the same direction and magnitude. Even you see two vectors, let's say I'll measure it, it's 5 inches, it could stand for 5 pounds. And another vector, and it looks like they're the same. But they have opposite directions. They're opposite vectors, so they are not equal vectors. A vector has magnitude and direction, so both have to be the same. The sum of two vectors is also a vector. A vector addition is commutative. A vector sum of A plus B is the sum. I'm not sure what other word he wants. It's the sum of vectors A and vector B. For every vector V, there is a vector negative V. Well, I was just talking about that right over here. I could have called this vector V, and this vector is negative V. That's opposite direction, and that's what we were talking about right here. The opposite direction. Vector negative V is the opposite of V. And the sum of V and negative V has a magnitude of 0 if you add those two up. Thus, it is the 0 vector. I'm looking before I move on here. That word I mentioned up at the top that he didn't have up in there, I said the word resultant. I may as well tell you what that is, because it would fit really good right here. That the sum of two vectors, I was redundant by using the word sum, but it makes more sense to say it's a resultant. I'll take that better. I knew resultant should be labeled somewhere, but it's a resultant of when you add two vectors together, it creates a third vector, and we call that the resultant. I'm going to run with that. Geometric properties of parallelograms to remind you about your geometry. This is a parallelogram. You call it a square. This is a parallelogram. You've called that a rectangle. All squares are rectangles. But this is not a square, nor is it a rectangle, and it's still a parallelogram. The reason that all three of those are parallelograms are because it's a quadrilateral, 4 sides. Opposite sides are always parallel, 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 parallel. They go in the same direction. Parallel, 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 parallel. Now I'm getting kind of bored, right? So are you, right? Parallel, parallel. And what else? The adjacent angles. That means the angles that are next to each other always have to be supplementary. That means these two angles add up to 180 degrees, always. These two angles will add up to 180 degrees, always. These two angles will add up to 100. Alternate means any two. And I just picked two. I could have picked those two would also add up to 180 degrees. The diagonals of a parallelogram bisect each other. Let's look at each of these parallelograms. If I draw a diagonal from that corner to that corner, and I draw a diagonal from that corner to that corner, they bisect each other. In other words, this distance here is identical to that distance here. This distance here is identical to that distance here. Even for the rectangle, it's the same thing. If I cut it, each of these pieces, this distance here is the same as that distance, I double tick mark, it's the same. And it's the same for this picture as well. These two diagonals bisect each other. This is important. When they do not necessarily bisect the angle. That's how I do it. Just because you cut the segment in half, that doesn't mean not necessarily bisect angles. This side could be bigger than this side. This angle could be different than this angle. So, could be. Maybe there's a special parallelogram where it is bisecting the angles. All right, example 1. We're going to find the magnitude of a resultant. Now remember what that means. If we're finding the magnitude of a resultant, that means we're adding two vectors together. And let's read the problem and I'll look at the picture. Two forces of 15 and 22 newtons act on a point in the plane. A newton is a unit of force that is equal to 0.225 pounds. So we use pounds in the English system, but we use the word newtons when we're in the metric system. If the angle between the forces is 100 degrees, find the magnitude and the resultant force. So let's look at this picture. It said that the forces were acting on a point. So what point did he mention? Didn't mention. Okay. So let's see. We've got a point PQ and a point PS. PS is the 22 Newton force, and PQ is a 15 Newton. So the length of this, you could call it 22, and the length of this, you could call it 15. The length is the scalar that describes the vector, and it's just a number, 15, and it's 22. Now, the direction of PQ vector is obviously not the same direction as this vector. So what happens is you have to imagine that if you were pushing something with force going this direction and then force also coming down, look at it like up here. You're at a point. Look at it like here. And your buddy comes up. Maybe it's a big desk. And your buddy pushes that desk from that direction. So obviously that desk might move straight. But then your other friend, who's not very helpful, because who knows where we want that desk to be, if you want that desk to be over here, then it'd be silly if your friend comes up here and starts pushing that. If that person is doing a 15 Newton and that person is doing the 22 Newton, well, unfortunately, the desk isn't going to end up over here because the 22-pound Newton outpowers a 15-pound. So the desk is not going to go to the right. As a matter of fact, you can look at this diagram and say, with a 15 force going this way and a 22 force Newton's going this way, that desk is moving this way. That's called the resultant vector. Which direction is that desk going to be moving, and how far will it go based on the forces that are being applied. Now, it's not like a continuous force where you keep on, keep on, keep on. It's a one-time force of 15, one-time force of 22, and now we're all tired. How far did that desk go? So when we have a resultant, the resultant is always a diagonal of the parallelogram, because we will imagine that this 15 Newton force this way has a parallel 15 Newton force underneath on the bottom here. Likewise, this 22 Newton force going this direction has a parallel to this side, forming your parallelogram. All right, so what are we wanting to do? Now that I explained to you the physics, if the angle between the forces is 100 degrees, that meant this up here. Between these two forces, it's 100 degrees. But that does not mean each of these angles are 50. And no picture is ever drawn to scale. So even if it looks like they're the same, you can't assume it's the same. Okay? So we're going to have to, well, they did us a favor. At least he added that as an 80-degree angle, meaning that's 80. Where did he get that from? Where did the author, how did he know that angle is 80? Because what we're going to do is find the length of this diagonal, which means, because I have two triangles here, pick a triangle and solve it. That's what we're going to do. But why was he allowed to say this has to be 80? Remember one of the rules we had about parallelograms? That the adjacent angles, this angle and this angle, will have to be supplementary. So angle P plus angle Q have to be 180. So that makes sense. You've already used up 100, there's an 80. As a matter of fact, do you remember the rule about quadrilaterals? Quadrilaterals have 360 degrees. So what if you said this? This is 180. This is 100, and this is 100. That adds up to 200. How much more do I need to get to 360? 160. Well, what's half of 160? Half of 160 is 80. So there's another way of also realizing that's an 80. Now, here's the interesting thing. If we have that's 100, that's 180. What can I do with that? You just had a lesson 3, called Law of Cosines. I'm looking for this side right here. I'll call it C. I have the angle across it, and I have the two, what we call those the included angles. That's the included angle. And these are the sides that are including it, the legs that have it. So law of cosines say, well, I'm going to call it what it's called in this picture, P, and he labeled that R, PQRS, going clockwise. So let me just do it with his notation. I called it side C, but it's really, we're going to call it V, because he called it V there. So we'll say V squared has to be equal to, he didn't give letters for the other sides. Let's just plug in the numbers. 15 squared plus 22 squared minus the 2 times the 15 times the 22 times the cosine of the angle included in the leg, which was 80. It's purely a calculator problem. So I would like it if somebody would key that all in, and I will go to my calculator and I'll key it in, and when I get done, I'll come back. Did you get it yet? Since the legs were whole numbers, I will put the rounded whole number. Approximately 594. So if you take the square root of both sides, vector v, and if we use the absolute value, guys, that actually means that's the magnitude. I don't think that came up in the vocabulary. You could say it's like, looks like absolute value, but it actually means the magnitude, the length of that vector. When I could also said the length of P R, PQR. I could have said the length of PR. I could have done that just as well. And I could have squared that and whatnot. So the vector magnitude squared gives me the vector V is the square root of 594. And I already typed that in my calculator. And I'm going to round it. Since they gave me all whole number newtons, I'm going to round it to whole number newtons. 20, was it 5? I can't remember. No, it's 24 newtons. 24 newtons. So all we found right now was the magnitude of the resultant. We didn't find the direction. That would involve finding the angle here, but we haven't done it yet. That's probably coming up in the next problem. Wrong problem. Oh, there's another one down here. The equilibrium. Okay, he's going to give us a definition for the equilibrium. 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 That's a tongue twister. Okay, I had enough fun pretending. What do you think equilibrium means? It's a vector that balances out a different vector. Just by looking at this picture, we have a vector from starting here going this way, and it has a magnitude. And he even labeled it V, see that? So then if you go 180 degrees and draw the same length vector to the left, negative V would be the equilibrium. Okay. So just looking at that picture, that's what I have. If I have this vector here, I'm going to erase this part in a minute. If I have a vector going out here, and he calls it magnitude of 48. If I draw the same vector 180 degrees the opposite direction, then that would also be a negative 48. You can almost say it's like it's a negative magnitude. And that's, where's my backup button? Here it is. Okay, I don't need to have that there, just to show you that any vector can it can be an opposite vector. He wants us to find the magnitude of the equilibrium of forces of 48 newtons and 60 newtons acting on a point A. So there's point A again. And he says if the angle between the forces is 50 degrees, then find the angle. So now we're actually going to find the angle between the equilibrium and the 48 Newton force. Okay, the magnitude will be the easiest to find first of all, because I got a lot of stuff in this picture. To find V. So I have two legs that have an included angle of 130 degrees. That implies that I need 50 for this angle. And technically, would I need 50 here? Let's see, 150 plus 50. No, I wouldn't. 150 plus 50 is 100 and... Oh, I'm sorry. That whole angle has to be 50. That whole angle is 50. So that's not helping me right now. All I care about is looking for V, using this leg of 48 newtons and this leg of 60 newtons and the included angle of this 130. So to find vector V again, so the magnitude of V squared will have to be 48 squared plus 60 squared minus 2 times 48 times 60 times the cosine of the included angle, 130 degrees. All right, so you're going to key it in. Hopefully you're doing it. And if I'm going too fast and you don't have it keyed in by the time I come back, pause the video. All right, like right now, I'm going to pause it and go do the calculator. Okay, I got the V squared, the magnitude squared. I'm going to round it. I have all nothing but whole numbers there again, so I'm going to round it up to another whole number. 9607. I better put approximately 9607, and that's got to take the square root to get v. The magnitude of v will be approximately the square root. I'll round that up to the nearest whole number. I think it was 98 newtons. Okay. Now, we still need to find the included angle that is found, that it's the, what do we want to find? The angle that is between the forces of 50. No, find the angle between the equilibriant and the 48 Newton force. Oh, okay. That's this angle right here, alpha. He's calling it alpha. This is the 48 Newton force acting on it. This is by definition the equilibriant. He told you it was, because that was V and negative V. I want to find that angle. Okay. You probably already know the answer. Maybe you don't. Let's play with that and see what we get. Go back to your first triangle. We have a lot of information here. I have an answer of 98 that goes right here, 98 newtons here. So now I have all three sides. I could do, to get what this angle, I want this angle. I don't want the whole angle. I don't want the whole angle. I want that angle, because that angle here is very powerful, because to go all the way from here to here, these two angles, alpha, let me give that a name. Let me call that angle beta. Let me erase something so you can see. Let me try to erase some of this. Okay, good. Let me erase that, and let me call that beta. Okay, if that was alpha, this is beta. So alpha and beta would have to add up to 180. Let's use law of sines. You don't have to be too picky. I want to have a side and an angle that are related to each other. So if I have this one right, I'm looking for this angle right here, beta. Sine, oh, my pen's gone. I'm calling it angle beta. Sine of angle beta. Well, beta's not really good because there's the b's up there and you might get confused. Let me call it angle. Let's use geometry. This lesson's about geometry. Let's use what we would have done in geometry. That would be angle CAB. Okay, angle CAB over 60. Let me just put. See, I don't know CAB. I know all of this, but I don't know this. So it's opposite is 60 equals 2. Let's pick. Now we got to pick. This is unknown, so I have to pick a side that is related to another side that I know. And since I just found out what this side is across, I can say sine of the angle. What angle is that? That would be angle ABC over the, what was my answer? 98. Now, that'll help me out. That's going to give me this beta that I needed. Sine of angle CAB will be sine of ABC over 98 times the 60. So I moved the 60 over. So, oh, why didn't I put in that ABC? That was 180. Let me type it in. Sine of angle CAB, the one I want, is equal to, oh, I don't know the answer. It's a sine of 130 degrees. 130 degrees over 98. Take that answer times 60. So when we get done, I want you to come back and give me Give me at least 4 or 5 decimals. Sine of angle CAB is, I'm going to go to my calculator. Make sure you're in degree mode. We're in degree mode. I'm back with the answer. Sine of angle CAB is 0.406900. And there's more decimals in my calculator, but I really want the angle. So what I'm going to do is my second of the answer. So use your calculator and do second of the answer in your calculator. I'm back. Second sine gives me approximately a 28-degree angle. Therefore, my angle alpha that was labeled up there will be 180 degrees minus the 28 degrees. That's 152 degrees. And this is approximate. That's approximate. That was approximate because I cut the decimals off. So did we find what he wanted? Find the angle between. You're right. Just find the angle between them. He didn't even tell us to find the resultant. Nope, we just wanted the angle between them. So we had all that work to do. Law of cosines and law of sines. That was fun, right? Okay, let's find, here's our first incline problem. Find a required force. Find the force required to keep a 15-pound wagon from sliding down. So if you're standing here holding that wagon, or you could be holding the wagon up here, you could be holding it here, whatever. You're either going to have the force going that way, or it's still going to go that way, still the same force. Do you either hold it from that end or you hold it from that end? So there's your idea of the force, but it's a 50-pound wagon, and we do know the incline is 20 degrees. It's labeled already, it's 20 degrees. And you need to realize that as that incline was higher, it would take more force to hold that wagon because you have something called gravity that's pulling it down. As a matter of fact, if I look at that plane, I have the gravity of that straight down, wherever the object is, straight down, doesn't matter where you draw this triangle, straight down is how gravity pulls you. And this is not metric system, this is the English system. So when we say 50 pounds, that's the force. That's the force. It's the same as if we do metric system, mg, where it's the mass times the force due to gravity. But when the English system, gravity is already taken into the account. That is why on the moon you have the same mass, but you have less gravitational pull, so you have less weight when you're on the moon. That's why they can jump so far. Now, the wagon here also is there's a force of the wagon straight down on the plane. This ramp, there's force from the ramp coming straight down perpendicular from it. So that's why you see a right angle here. And it should be made clear here that the force that's being used to hold that wagon up, it's a parallel force to the bottom of this triangle. So these two lines are actually parallel. And if you look at the labeling of his letters that he put, you've got a force vector BF labeled right here. And you've got AC, which is parallel to it. Now, there is some mathematics. If we're going to add vectors together, for instance, if I talk about BA, I could take the BA vector and it should be equal to the sum of the other two vectors. So that would be BC, but I can't add it to the AC because AC is going, I need the vector to be added together like that to add up to this vector. So I'm going to go add the opposite of AC. So I might need that equation later on. Remember what I said about BC was the force, because there's weight on the ramp, and therefore the ramp is being pushed down. So that's the force on the ramp. Okay, this is the force that the wagon has been given by gravity. Now I gotta look at the picture a little more. Let's look at some ideas of parallel lines. Since BF is parallel to AC, I'm going to extend it out, and I can call this a transversal. It's a line cutting both those parallel lines, and that's why this right angle is an alternate interior angle for here. There's your 290. And if we know this side's the same as this side, what else can I have? I can use another transversal. I can make this one a transversal. This BA is a transversal, also cutting the same two parallel lines. So that makes this angle equal to this angle. So if this angle is equal to this angle, and this angle is equal to this angle, would like to see that I have two similar triangles. This triangle and this triangle are similar triangles. Yeah, I didn't even notice he even labeled that this is a 20-degree angle, which is identical to this 20-degree angle. So yeah, they are similar triangles. So the whole point is I'm trying to find the force. So I just need that value here, which is the same as whether it's up here, it's the same value up there. Okay. It looks like I could probably use the law of sines, because I have that angle there. I can say sine of ABC, angle ABC, over AC, that's the magnitude of the vector of AC that I want, would be equal to sine of angle ABC. Well, I already have ABC. That's that ABC is 20. So that's, what would it be, over? I can use the right angle here over the 50. That would be sine of angle ACB. This was ABC, ABC. This is ACB over 50. Plug in the numbers. Sine of 20 degrees over magnitude AC, which is what I want. That's the force. Sine of 90 degrees over 50. What's the sine of 90? What's the sine of 90, guys? Right triangle? No, we use this way. We do sine of 90 is up there. The ordered pair is 0, 1. It's a 1. So it gives me, let me get what I want up front. What I could flip those to make it easier. I could say AC over sine of 20 degrees equals 50 over the 1. That's a lot easier. Then I can say the answer that I want is sine of 20 degrees times 50. That's what I will want to find out. So type that in the calculator. I'm going to count to 20 and let you come back with the answer. One, I got AC is approximately, I'll round it to a 17. That would be 17 pounds of force. To hold that, how big was that? Wagon, 50-pound wagon. And it would need more force if the wagon was steeper. All right, another incline plane. You know, everything in this picture is going to be identical to what we just talked about. You're going to have a parallel, parallel, transversal, alternate interior, alternate interior. You're going to have a different transversal. Cut that with a different color. A different transversal where that angle will equal that angle. Just keep that in mind. And then obviously you've already can determine you're looking at two similar triangles again. So let's see what he has. This is a force of 160 pounds. No, I'm sorry, 16 pounds is required to hold a 40-pound lawnmower on an incline. So it's the same as the other problem, except this time I don't know the angle. I know how much force I need. I need 60 pounds to hold a 40-pound. It's kind of interesting. It's very similar to the last answer. I needed 17 pounds to hold 50. It's about right. So I'll bet you any money our angle's not too far off from the 20 degrees. I'm just guessing, okay? So we're going to make this happen here. He didn't draw the lawnmower. Just draw the lawnmower. You know, every lawnmower. That's going to have big wheels and it's going to have something to hold on. Okay. It looks more like a stroller. I'm not a very good artist. Okay. We have vector BE representing the force to pull that lawnmower, hold it in that direction. The force could be even coming from over here by you standing there next to it, right, and holding it. The same force. It doesn't matter where you draw. It's parallel, same magnitude, and it's also parallel down here, but it's going in this direction. And so that's we're looking. We're not looking for the force. We didn't know what that force is. Just like in the other problem, we're going to find out that we know that this angle here is also theta. It's going to be the same angle because you're going to have, look at, you've got angle, angle, angle. It's a similar triangle. Three angles that are the same. Angle, angle, angle. We need a side though. Do I have a side? Oh, I have a side. No, I don't have a side yet. Well, let's go ahead and find the angle with the law of sines again. We did on the other problem. So I got this angle here that I was interested in. And I don't have another angle. Hold on here. Oh, yes, I do. I still have a right angle. I keep forgetting. I can say this angle pairs up with 40, so I go sine. I like shading color. Sine of 90 over the 40 has to equal to, let's go for this angle here. And I'm telling you, it was theta, remember? Sine of theta, I don't know, over 16. Sine of 90 is a 1 again, so 1 over 40 equals to sine of theta over 16. So basically, sine of theta is 16 over 40. And so you're going to have to get the decimal number and do second sine. You're going to do the second sine of 16 over 40. And that'll be approximately, I'm going to go do the calculation. 23.6 degrees. I did tell you it was going to be very similar to the other one. And I'm about done. I put this slide in here because I saw it in a PowerPoint, but I didn't see it defined very well. I might find out there really is. Airspeed of a plane is how fast it is going in the air. It's relative to the air, but ground speed is relative to the ground. So you can see that a plane could be flying like that, so it has an air speed, but ground will apply to straight across flat on the ground, no matter how fast the plane is going up that way. It's not the same speed horizontally. The combination of the vertical and horizontal creates this vector here, but the miles per hour on the ground this is going to be more miles per hour because it's longer. The ground speed of a plane is represented by the vector sum of the airspeed and the wind speed. So picture it's in our book, and it also is in it's also in our PowerPoint. You got a plane that has bearing and airspeed. Bearing is the direction because you have this angle here. So even if you draw it out from it's an angle. Direction is always the angle. Wind speed, you got the winds pushing on the plane as the plane is flying this way. Therefore, it causes the plane to actually go not straight this way here because the wind's pushing it. So you got your air speed, you got the wind speed, and it creates a new bearing for that plane. So if the plane wants to go somewhere, they have to take into account the wind speed. Maybe the plane comes up after. Example 5, applying vectors to a navigation problem. This is a ship. It has we didn't do that. We didn't do a plane. I don't know if I want to. So I got ahead of myself where that picture was. Applying vectors to navigation. So look at the picture here. Navigating due north. We've talked about northwest angle and how far it could go. We could talk about making a turn to go east. Okay, so all those things we've talked about before. A ship leaves port at a bearing of 28 degrees. So look here. When we say bearing of 28, you're going north, but your bearing is 28 degrees from the north. That's 28 degree angle. So I'm moving. And I'm traveling 8.2 miles. So once I get to 8.2 miles, it looks like the ship is turning. There it is. The ship is turning due east, means no matter what angle I was going, I'm now going to go, whatever the compass says where east is, I'm going to head east. So it turns out that he has to make a 118 degree angle this way, turn that boat around to go from where it was here to here, 118 degrees. Now he's going to travel only 4.3 miles. Okay. How far are you from the, how far is the ship from the port? What is its new bearing? So you're looking for the resultant vector, this one right here. And that'll be the easiest to find first. Let's find that first. I think that would probably be the easiest way to go. Trying to think, is there an easy way to do it without having to... I don't have any complete angles. Okay, let me erase my chicken scratch. Oh yeah, I do have that angle here. Well, that's interesting. This is definitely a right triangle. I think I'm that drawing. This is a right triangle. So we could find that angle to go with it. But we'll do that after. Let's find this measurement here. Too bad I don't have this measurement. I don't have that measurement, or that'd be a good... I have this measurement. I could add it to that, but I'm just going to use... I have two legs. I have an angle. I can use law of cosines. PE, the magnitude of PE has to be squared, equals to the 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 cosine of 118 degrees. Okay, I paused it. Did you go and do it in your calculator? I have why do I change it to that? PE magnitude squared is approximately, let's see, I have decimals in the problem. I have two decimals here, 20 and 30, so I'm going to use two decimals. 119.84, take the square root, and you find out that the magnitude of the resultant is 10.9. That means that's how far I am. I'm 10.9 miles now away from the beginning. That wasn't too hard. Now to find bearing is, we're actually looking for, I need this total distance here. That's my bearing to go to here. So I have part of it. I don't have this part here. So I might be, look, I think I could use, to find this angle here. Yeah, I can use law of sines. So I can say, I'm looking for sine of APE. He's an ape. And that is over the 4.30. So 4.3. Pick another angle. Sine of the 118 degrees over the last answer, the 10.9 that I just did. That'll work out fine. So sine of the monkey is equal to 4.8 times sine of 118 over 10.9. Is that what we had for an answer? Yeah, 10.9. So sine of that. So you're going to have to get a decimal answer and then do arc sine of this is what we're looking for. So arc sine of that, you can do it all in one step. Second sine, then put the math in it, hit enter, is approximately, I'll give you a couple seconds. $20.4, and I'm going to use the one decimal only because he used, what did he use in the other decimals? He used 118.0. You see, when he says 0.0, that implies one decimal of precision. So 20.4 degrees would be my bearing. No, that's not my bearing. That's just this angle here. My bearing, total bearing will be from the first original, from going due north, will be the 20.4 degrees plus the, was it a 28 degrees? So 48.4 degrees. And of course, that does mean from the due north. To do a plane. Yeah, airplane's at 6. Okay. Okay. I think I'm going to let you go with this one here, and we'll. It's a very complicated problem. You got two sets of coordinates because he's talking about the wind speed and airspeed, and it's already late. So I'll do a separate one and just submit it. Actually, I don't have to. The other day I posted the whole video of this lecture already in your It's Learning. So you can go ahead and get it from there. I'm tired. Bye.